The problem is from grade 2018 mathematics paper, question number 43. The problem given is, let f of z equal to z cube times e to the power of z square for z belongs to complex numbers, and let gamma be the circle z equal to e to the power of I theta, where theta varies from 0 to 4 pi. Then 1 divided by 2 pi I times circle integration over gamma f dash of z divided by f of z dz equal to dash. So the NPTEL reference to solve this problem is Module 1, Lecture 2 of Advanced Complex Analysis, Part 1. The title of this lecture is The Argument Principle, Roche's Theorem, and the Fundamental Theorem of Algebra by Dr. T.E. Venkata. He is from Department of Mathematics, IIT Madras. Even you can watch this lecture using this YouTube link. So now coming to the solution, by just looking at this integration, the type of integration, that is f dash of z divided by f of z. So the one theorem you should remember is argument principle. So whenever you see an integration of this form, f dash of z divided by f of z, the only theorem you should apply, not only the theorem you can apply is the argument principle. Even if there is any multiple of some f dash of z divided by f of z, even in that case also the theorem you should apply is the argument principle. In that case, you should apply an application of argument principle. So now for this problem, since it is given f dash of z divided by f of z, so we apply the argument principle. Given that f of z equal to z cube times e to the power of z square, z belongs to complex numbers, and gamma is the circle z equal to e to the power of I theta, where theta runs over from theta varies from 0 to 4 pi. So firstly, let's look at the circle and then we'll come to the argument principle. So for that, by just looking at the circle that is given as, so when I assume this is a circle of radius 1, so then the curve or the circle gamma is given as, so when you run the values from theta from 0 to 2 pi, the circle you get is the same circle e to the power of I theta is equal to 1. So when you assume the theta runs from 0 to 2 pi, you get the circle as the circle of radius 1 centered at 0 as rounded one time and in anti-clockwise direction. So, but when you assume the values of theta from 2 pi to 4 pi, you can say the circle z equal to e to the power of I theta runs along the same circle mod z equal to 1 and in the same direction again. That means when you run the values, value of theta from 0 to 4 pi, the circle runs along the curve. The curve gamma runs along the circle twice. That can be seen from these values of theta. So what does this means is, okay, firstly let me write the argument principle, then you can understand. Mhm. So by argument principle we have argument principle tells us that 1 divided by 2 pi I times integration over gamma f dash of z divided by f of z dz is equal to n minus p. But here what is n and p? Where n is the number of zeros of f of z inside gamma, and p is the number of poles of f of z inside the same gamma, of course counted with multiplicities. What does this counted with multiplicity means? Suppose there exists a zero or a pole of the same function f of z which is repeated twice, then the multiplicity of that function is 2. That should be counted as the multiplicity. And whenever it is a triple zero or triple pole in the sense, or zero in the sense, the order of that pole or zero is 3. That is counted as multiplicity. So now by using this theorem we have integration f dash of z divided by f of z dz over the circle gamma, that is as 2 pi I times, or since gamma is written z times z equal to e to the power of I theta, where theta is from 0 to 4 pi. So this is 2 pi I times n minus p, where n is number of, okay, let me write that in next claim, where n is the number of zeros of f of z inside gamma, and p is the number of poles of f of z inside gamma, of course counted with multiplicities. So from this we can see, or firstly let me write one more thing, the integration f dash of z divided by f of z dz over z equal to e to the power of I theta, 0 is less than or equal to theta is less than or equal to 4 pi, which is what we need, which can be written as integration f dash of z divided by f of z, z equal to e to the power of I theta, 0 is less than or equal to theta is less than or equal to 2 pi, this times 2. Since wherever Whereas I'm considering in the first integration the circle is the same circle z equal to e to the power of 5 theta, wherever the theta is running from 0 to 4 pi. That means the circle is running along this circle, along this boundary of this circle twice. But whereas coming to the second integration, the circle is same circle and it is running, theta is running from 0 to 2 pi. That is, the theta is running from 0 to 2 pi. That means we are considering the circle in the second integration as the same circle, but it is running only one time. So whereas coming to the first integration, since it is running two times, I can multiply the whole integration with 2, but I'm changing the curve or the circle up to the range from up to the range of theta from 0 to 2 pi. The values of both the integrations are same. So now by using this, we can say, so integration over gamma f dash of z divided by f of z dz equal to 2 times 2 pi I times 2 into 2 pi I times n minus p, and where n and p are the number of zeros and poles of f of z. It lies inside gamma only. Whatever the circle, whatever the zeros or poles outside gamma, it does not matter. So the only poles and zeros inside this gamma we consider. Since f of z is given as z cube times e to the power of z square, so we can easily calculate the number of zeros and poles of this function. So from this, by just looking at the function, we can see which is entire. Since e to the power of it exponential function is always, since e to the power z square is a polynomial which is analytic everywhere, I mean which is entire, so e to the power of z square is again entire, and since z cube is entire which is a polynomial, since, so in total the whole multiplication is entire function. So from this we can say the function f of z is entire and hence it does not have any poles. So it does not have any poles. But the question here is, what are the number of zeros? So from this we can, since f of, sorry, since exponential function is never zero for all z belongs to C, so f of z equal to 0 implies z cube equal to 0, and hence, so in the case whenever f of z should be 0, the only possibility is z cube should be 0, and hence the only zeros of f of z are here, the converse in the sense the reverse condition also true, since exponential function is never 0, f of z equal to 0 if and only z cube equal to 0, and hence the only zeros of f of z are z equal to 0, which are nothing but the zeros of the function z cube equal to 0, and with multiplicity 3, since we can see z cube is a polynomial of degree 3, so hence integration f dash of z divided by f of z dz over gamma equal to 4 pi I times the number of zeros, that is equal to 3. Hence in total this has 12 I. But okay, since it is asked that 1 divided by 2 pi I times integration f dash of z divided by f of z dz. So it is nothing but 6. Hence the answer is 6.